These days, the term world model is totally overused. An AI that can generate cool videos is called a world model. A physics simulation engine, like those from Nvidia or Tesla, is also called a world model. And even digital twins dare to call themselves world models. It's the same name, but what's inside is completely different each time. This kind of chaos in the market made Fei Li, who works on world models, unable to sit still. So Fei Li and her team specifically wrote an article for one purpose, to clarify what a world model actually is. The article opens with a particularly bold statement. The world is not made up of words. This applies to large language models. They allow machines to grasp concepts, vocabulary, and even reason remarkably, but the physical world follows a different logic. Language models learn patterns in words, while world models must learn patterns in space and time. How does light fall on the surface of an object? What does a garden look like from an angle that's never been photographed before? What happens when you push an object? How does it move? How do you obey the laws inside a house? These two things are fundamentally different. So how do you set rules for this kind of chaos? You have to go back to a diagram that's much older than these technologies, the loop that's been used in reinforcement learning textbooks for decades. It's about an agent, which could be a person, a machine, or software, making an action, and that action changes the state of the environment. But the agent can never actually see the state itself. It can only see observations, like the readings from the light that falls on the sensors in the eyes or the pixels in a video. New observations lead to new actions, and the cycle repeats. The formal name for this diagram is the partially observable Markov process. Markov decision process, and the original definition of the term event model also comes from this. There's a word here we need to clarify, state. It refers to the complete underlying truth of the world at a given moment. Every object, every position, every velocity, every attribute is included in it. The state is the true nature of the world, complete in principle, but no one within it can directly see it. What we can see is always just a partial projection of it. Once you understand this cycle, you'll realize that all those messy design models are actually just different facets of this same cycle, each only outputting a part of it. Based on this, you can neatly divide them into three categories. The first category is called renderers. What it outputs are pixels for the human eye to see. The main focus is on how good the visuals look. For example, a video model that turns text into cinematic camera movements is a renderer. So what's its problem? It doesn't actually understand three-dimensional structure at all. What it generates is what you would see, not what actually exists. There's a particularly accurate example. A city shot by a drone from above looks flawless from the sky, but if you try to drive through that city, it falls apart immediately because the buildings are fake. They just look real. The second category is called simulators. What it outputs isn't an image, but a state. A physically and geometrically realistic structure is unique. Renderers only need visual accuracy, but simulators need more. Geometry and physics must be precise, and motion must follow real-world dynamics. It serves two types of clients at the same time. One type is professionals like architects, designers, and filmmakers who demand a level of realism and detail that goes beyond just looking real. The other type includes robots, autonomous driving systems, and similar programs that use the simulator as a training ground to run experiments that would be too dangerous, too expensive, or simply impossible to conduct in the real world. The third type is called a planner. What it outputs are actions. You give it an observation and a goal, and it tells you what to do next. In fact, this is like a renderer, but in reverse. A renderer takes actions and generates images, while a planner takes images and generates actions, closing the loop from perception to action. So now, those giant AI models for robots are essentially all acting as planners. Among these three types, which one is the most important? Here's a counterintuitive judgment. The simulator, which gets the least attention, is actually the most important. Renderers are the most mature. The market is already huge. For example, Google's image models are used by hundreds of millions of people. But there's a ceiling. They only optimize for visual appeal, not for physical accuracy. So no matter how beautiful the images are, you can't use them to design a building or train a robot. Planners are the most enticing, but also the least mature. Just look at those robot demos from the past 2 years. The videos look really impressive, right? But to be honest, almost all of them are done in extremely narrow, controlled lab settings. We're still a long way, miles and miles away from having a robot that can reliably work in a real kitchen, warehouse, operating room, or factory. And the simulator is the bridge that connects both ends. There's a particularly weighty saying here. If language is the abstraction of the world, pixels are the projection of the world, while geometry, physics, and dynamics are the world itself. A model that truly masters simulation can project its understanding into pixels for people to see, and also into actions for machines to interpret. But a model that can only render or only plan can't really do either. That's why the simulator is the backbone of the whole thing. The most important player, NVIDIA's Omniverse, is targeting a market worth over $1 trillion. Almost every robotics company is relying on simulation for training, digital twins of factories, warehouses, and supply chains. It's all riding on this. But simulators are also the toughest nut to crack. Three-dimensional data with geometric and physical annotations is even more complex than what renderers deal with. Internet videos used for training? They're several orders of magnitude more scarce. And then there's that unavoidable gap between simulation and reality. Things just don't perform the same in simulation as they do in the real world. We've talked about this over and over again in our previous videos about robots. What's even trickier is that AI-generated geometry might look correct, but inside it could be glitching through itself, the dimensions could be all wrong, and the resulting physics is just a mess of weird curves. So where are these three categories headed in the future? The answer is they're actually merging into one, because rendering a world and simulating actions within it both require the same underlying knowledge. Take that cup, for example. A model that truly understands how a cup sits on a table should be able to draw it from any angle, simulate how it would tip over if you pushed it, and even plan how a hand would pick it up. These three things are actually three projections of the same underlying understanding. So what's the ultimate goal? It's a unified design model, a foundational model that can render photorealistic images, produce physically accurate structures, and plan the sequence of actions needed downstream. In essence, it truly understands what the object is. This is the core of the field today, and also its most challenging open problem. The significance of this goes far beyond the technology itself. Since the late 1980s, this field has been betting on the same thing, that a sufficiently rich world model is what an intelligent agent needs to perceive the world, create within it, and act in it. All of it. Today, three lines of development that used to be independent, and each already a $100 billion industry, are starting to operate as if they're the same thing. In the end, language gives machines the ability to talk about the world, but it's the world model that allows machines to truly understand, imagine, reason, and actually interact with the world. That's the end of my reading of Fei-Fei Li's original article. I've posted it in the main group on my homepage. Follow me, and I'll see you next time.